Bezout's identity can be used for different purposes. In our case, it is most relevant when we want to find the inverse of an element in one of our algebraic structures that we will define later. The theorem for Bezout's identity is as follows. If we have n1 and n2 and these are two non-zero integers, then there exist two integers that we call s and t, such that the greatest common divisor between n1 and n2 can be written as s times n1 plus t times n2. And the numbers s and t here will not be unique. So let us derive Bezout's identity. Recall that from Euclid's algorithm, what we did there was to use Euclid's division theorem to iteratively write the remainder in this way. So what we can do now is that we take Euclid's algorithm and then we rewrite the different steps in the following way. So the first step we can rewrite as r0 equals n1 minus q0 n2. And in the next row we can rewrite this as r1 equals n2 minus q1 r0. Then we can rewrite this one as r2 equals r0 minus q2 r1. And we continue like this, and here we rewrite this one as ri minus 1 equals ri minus 3 minus qi minus 1 ri minus 2. And the next one we rewrite as ri equals ri minus 2 minus qi ri minus 1. And the last one we could write as 0 equals ri minus 1 minus qi plus 1 ri. And when we did Euclid's algorithm, our goal was to find the greatest common divisor, which was ri in this case. So we wrote here that GCD of n1 and n2 equals ri. But what we can do now is that we can go backwards through this algorithm and start with the second last row, and we can write ri equals ri minus 2 minus qi ri minus 1. And what we do here is that we now iteratively go upwards towards r0, and we replace, first in this case we replace ri minus 1 by the expression that we have here. So we rewrite this as ri minus 2 minus qi, and now ri minus 1 can be written as ri minus 3 minus qi minus 1 times ri minus 2. And now we see we have written this as only ri minus 2 and ri minus 3. So then we continue upwards and we replace ri minus 2 with the preceding row in this algorithm, so the row that would have been here, and then we replace ri minus 3, ri minus 4, and so on until we reach the end. So we will have something that we now call s that we can multiply by n1, and we have something that we call t that we multiply by n2. Because in the last step in this algorithm we have replaced r0 by only something that contains n1 and n2. Let us try this for the numerical example that we had for computing the GCD between the numbers 1311 and 391. The first thing we do here is that we rewrite the rows as, in this case, 138 equals 1311 minus 3 times 391. This one we rewrite as 115 equals 391 minus 2 times 138. and this one we rewrite as 23 equals 138 minus 1 times 115. And we don't need to rewrite the last row because we're going to start from the second last row anyway. So here we have that the GCD of 1311 and 391 is equal to 23, so we can rewrite this as 23 equals 138 minus 1 times 115. So now we're just repeating the second last row that we have here. Now the next step in this algorithm is to go to the row above in Euclid's algorithm and we replace 115. So this equals to 138 minus 1 times, and 115 is 391 minus 2 times 138. Now we collect our 391 and our 138s, so this can be written as minus 391 plus 3 times 138. What we do now is that we go to the next row in line. So here this is going to be written as minus 391 plus 3 times, and now 138 can be written as 1311 minus 3 times 391. So now we collect our 391s and our 1311s. So we have 3 times 1311, and we have minus 1 here, and we have minus 9 391s. So we will have minus 10 times 391. So we have now written our GCD 23 as S times N1 plus T times N2, where S equals 3 and T equals minus 10.